Hello and welcome to the basics of protection relay testing. I am Saravnan, the CEO of Minatal Power Systems Private Limited, Chennai. So first of all, I would like to welcome all of you and say a happy Sunday. And for those who know me, hi, how are you? And for those who do not know me, I am Saravnan, the CEO of Minatal Power Systems. So we are a protection and a reliability consultant wherein we mainly perform the design, analysis, testing and commissioning of power systems. So I have more than 8 years of domain experience in various parts and various sectors of power systems, including design, testing and manufacturing. We are also involved in the training and research and development projects with respect to different academic institutions. And on a personal level, I have a master's in power systems and I am currently pursuing PhD in the field of power system protection. Now, power system protection, I would be lying if I say that power systems was one of my favorite subjects. In undergraduate, I didn't like it so much, but once I've completed with my undergraduate, this became the love of my life. So to start off with, what are we actually going to be doing today, right? So I want to talk about a bit about the basics of protection, protection from my perspective, so that to give you a very generic idea of what we will be looking at and what the terminology is. We'll also be trying to look at a bit about relay configuration. We have a couple of softwares with which we can see how a very simple relay configuration is done and how it varies from manufacturers. We'll also be talking a bit about the test setup and the plan. So we have an Omicron CMC over here, and we'll be talking about how to set up your test kit. How do you plan for a particular testing of any particular protection relay? And to close off with, we'll be looking everything from determining what is your connections to calculating what is your injection parameters, all the way to see how testing needs to be done and how do you actually record the results, right? So this is what we will be seeing in the next hour or so. So to start off with, thank you for everyone for joining me today. And I am Saravanan, And this is the basics of protection relay testing. So what is power system protection? So when we always talk about power system protection, we say that power system protection is an insurance for system and power availability as well as system reliability. So when we talk about availability, we always say that, okay, the powers, there should not be power cuts, right? It's as simple as that. But more importantly, you also need to identify which part of the system should be available at what times, and also you need to ensure that the system is reliable enough. So in case of faults, it is always necessary to isolate a part of the system, but also be very specific about which part of the system are you actually isolating. So when we look at protection system, right, so we already know that the objective is prevention and control of system failure, right? So you not only want to prevent system failures, but you also need to control the level of failures that could happen and minimize the effects. So I would like to see this in two ways. So one classification is what we call as reactionary devices, and the other one is safeguard devices. So reactionary devices from a particular perspective is supposed to recognize a hazard or recognize a disturbance or recognize any given fault within your power system, and you're supposed to take a predetermined action to remove the hazard. So a key thing to note over here is that you not only need to recognize a fault, you not only are supposed to recognize the disturbance, but you're supposed to take an action to remove the disturbance. So one of the best example is our protection relays. So protection relays are not only configured to recognize a particular event, for example faults, but they also have to take an action that is predetermined based on the configuration that we set to remove the fault. How does it remove the fault? It isolates the faulty part of the system using circuit breakers. So a protection relay recognizes your hazard and it trips a circuit breaker to isolate a part of the system. So the next type of devices is safeguard devices. So safeguard devices, they also recognize events. They also know when an event is happening, but they take an action to make sure that the environment is less hazardous, which means they do not usually isolate, they do not remove a hazard, but they make sure that the environment is less hazardous. So one of the best examples for a safeguard devices is your automatic voltage regulator. So your AVR that is connected to your transformer tap changers or OLTCs, they know whenever the voltage is above or below a certain limit, but they do not trip a transformer. They do not make any changes. What it does, it either changes or it takes an action to ensure that the voltage is within certain limits. So there's no isolation, there is no tripping when it comes to safeguard devices. So in the rest of the program, what we'll be looking as reactionary devices, because our focus is mainly on protection relays, right? So how do you actually trip a device? How do you actually isolate a device? So very simple, you measure certain parameters, right? For every fault, for every system disturbance, there is going to be a signature that you need to know. For example, if you consider any simple short circuit, the most common signature is overcurrent, right? So the current becomes abnormally high whenever there is a fault. So people decided to use this parameter, that is the current measured, and they just check two parameters, two constraints. So first constraint is inequality. Is my current above a certain limit? Yes. Then it becomes an abnormal state, right? So it's not a normal condition because I know that my current is above a certain value. And if it exists in that particular state, or if the current is above the setting value for a particular time, then I trip. Then it results in an outage. So it's very simple. You have two constraints. One, the parameter checks whether its value or the measured value is greater than a setting value, and if it is present for a time greater than a setting time, right? So this is very simple, a generic way of looking at protection relays. So if I were to draw the operation of a protection device, what do I get? I essentially have a comparison element in the heart of it, right? So a comparison element just compares two quantities. One, it is the metered quantity or your measured quantity, and it compares that with your threshold quantity. So in case of overcurrent relays, your metered quantity is your current from your current transformers, and your threshold quantity is again going to be your current setting that you give, right? So it compares both of them. Now, if it is greater than the threshold quantity, if the measured quantity is greater than the threshold quantity, then it goes to the decision element. So in the decision element, it measures or it checks the time. So is the metered quantity greater than the threshold quantity for a particular amount of or for a particular time period? So if it is greater than a particular time period, it goes to the action element wherein you aim to trip the circuit breaker, or if it becomes less than the threshold quantity, then it resets. So here you can think of two things. One is what we call as pickup, and other one is what we call as trip. So pickup is when your comparison element is enabled, right? So comparison element is enabled when your measurement quantity is greater than your threshold quantity, and if your current is greater than your setting current, then the relay picks up. Now after a particular time, the relay trips. Now during pickup state, if the current goes below the threshold quantity or below your setting quantity, the relay drops off. So these are the states of your protection element. So like I said, for you to understand what are all the possible events that you need to think of before actually protecting a system. So you can't just go and say, I want to protect your system, and we say that, okay, let's use overcurrent protection or let's use distance or differential protection, right? You need to understand what are all the possible events that could happen within your system, and what are all the possible disturbances that could happen. What could be the effect of those disturbances? Based on that, you design your protection system. So something simple like tripping of a load can result in an overfrequency. But the same overfrequency, when you are tripping it on a generation side, right? When a huge amount of load trips on the generation side, then you know that there is going to be overspeeding of your generator, right? And if a particular line trips, it is not only necessary that only that line is going to trip, it can result in cascading effects. So I think people would remember the 2012 outage that happened in New Delhi. So that happened because of a mal-operation of a distance protection relay, which resulted in one line to trip. So you can see that a line outage as a system disturbances can result in instability and blackouts because parallel lines also get overloaded. It can have some cascading effects which can result in a trip. So it is not only necessary for you to understand what is going to be the events that is going to happen, but you also need to know what are all the possible effect of those events as well. So there is an art of protection. So when we talk about protection design as well as protection testing, we usually ensure that we have maximum and reliable protection at minimum equipment cost. We have a high sensitivity to internal faults, which means that the relay should pick up as soon as the parameter exceeds the certain setting value. But at the same time, we should have high stability during external faults, which means that for the highest amount of fault current outside your protection zone, your relay is not supposed to operate. At the same time, you also need to have high speed fault clearance with correct selectivity, which means that the relay closest to the fault should operate first, and it also should have the ability to operate correctly under all predictable power system conditions, which means as a protection engineer, you should know what are all the possible power system events that could happen before you actually protect your system, right? Okay. So jumping into protection relays, right? So here I want to ensure that we cover protection relays in a very generic way, because if I focus on overcurrent protection, then we'll be learning only about overcurrent protection, but I do not want that, right? So I want to ensure that we have a very generic way of looking at protection relays. So what is protection relays, right? So in the heart, it is a black box. Let's consider it as a black box because it's just a piece of hardware which has a functional logic within it. Now you have certain input energizing quantities. So what are your energizing quantities? Your measured values. So your measurement values are nothing but your current, your voltages, those form your analog inputs, right? You can also have a certain level of binary or digital inputs that could either represent blocking signals or it could represent any inputs, user-defined inputs to your protection relay, right? And on the other side, that is on the output side, you can have multiple binary outputs or digital outputs, but the most common one is trip output, right? So your trip or operating signal is what you would use to give to your circuit breaker, right? At the same time, you can also have a start signal or a pickup signal. So the moment your measured quantity becomes higher than your setting, then the start signal is generated. So on top of all this, you have the functional logic. Now the functional logic is what is going to be varying from relay to relay, right? So how the input quantities are combined with each other, how the inputs along with their input quantities and analog quantities, how they combine with each other to give you the start, the trip or other binary output contacts. In old generation electromechanical relays, these functional logic itself used to be in as a hardware, right? But now in numerical relays, in IEDs, you know that these are completely configurable up to you. So a bit more into the functional logic. Let's go one step deeper. So what does it actually do? What does the relay actually do? So please understand that this is a very generic way of representing. There is no manufacturers. Every manufacturer has their own way of own algorithms, own functional logics. But generically speaking, the input quantities go through a concept of signal processing. The algorithm for signal processing may vary from manufacturer to manufacturer or even between relays and relay models. Then it measures a particular quantity. So in case of overcurrent relays, if I want to measure only the fundamental value, then what is the signal processing? So we use Fourier transforms, we use DFTs or FFTs to give you the fundamental quantity, and that is the quantity that is actually measured, right? And along with your binary inputs, you can create some kind of operational logic. Operational logic would involve some kind of interlocking, and you can also create any additional restraint or blocking for your protection element. At the heart of your protection relay is going to be a comparison element, right? So like we already said, the energizing quantities along with your binary inputs would give you a certain level of operational logic and measured quantity, but it will be compared with a certain settings. It can be one particular parameter or it can be multiple parameters. And if the comparison element is enabled or it becomes high, then the pickup signal or the start signal is generated and the timer is started, right? Now in a lot of protection, the timer may be set to 0. It can be instantaneous, but generically there will be or there can be a timer. Once the timer has elapsed, then the operate signal is generated. Now the operate signal that we see over here is something that is used to trip the circuit breaker. Now pickup signal can be used in case you want to know when a protection relay has protection element has picked up, but the operate element is what is used for tripping your circuit breaker. Okay, moving ahead. So we have talked about what is the functional logic that is within the relay. Now let's see what is relay configuration itself, right? So what is relay configuration? So we have talked about the different parameters, right? But more importantly, there are 4 main things that you need to configure. So the first one is going to be your input configuration. That is your binary input configuration. So here you will be configuring your blocking signals, your status signals. So blocking signals is in case you want to block a particular protection element or in case you want to block a particular output, then you can configure it as a blocking signal. Now status signals can be status of your equipment such as circuit breaker status, disconnector or isolator status. And on top of this, you can have any other user defined inputs. So in case you want to carry forward a particular input of, let's say, a mechanical trip of a transformer through the IED, or given it as an input through an IED, then that also could be a part of your input configuration. The next one would be your output configuration. So when we talk about output configuration, we talk about your trip signals, that is the operate signals for different protection elements. So you can have a general trip signal in which all the protection elements will be assigned to one particular output, or you can have individual trip signals. You can also have status signals as outputs, and you can have any blocking signals in order to take it forward. And again, you can have any other user defined outputs as well. Now, on the side of your analog input configuration, here is where you will configure your current, voltage, or any particular transducer inputs. So when we talk about current and input and voltage input, we will be referring to configuring what is the way they are connected, what is the CT ratio, and what is the usage of the analog inputs within the relay. And on the logic side, you will be configuring what is your protection logic, that is how a protection element should operate, what should be its behavior, what should be the trip logic or the blocking logic, and more importantly, in some cases, you'll also be configuring the interlock logic. So interlock logic in such a case would be your interlocks for your breakers opening and closing, interlocks for your earth switch, and isolators as such, right? So you can have a very exhaustive set of configuration within your protection relay, but it all depends on what you want out of the protection relay, what is the functions, what are the elements that need to be configured within a protection relay. Now, relay configuration, like we know, it varies from manufacturer to manufacturer. Now, a lot of manufacturers use their own software tools, but from a very generic perspective, the relay configuration is predefined based on your operational practices. It is based on the type of protection that we use, and it is also based on the input, that is analog or digital, as well as your output requirements, right? So with this is just the theory part. Let's just go into a software and we can see configuration. So today we will be working with two software. One is the eSurgy Studio from Schneider, and the other one is the PCM 600. So I will be showing you a very general overview of what is included as a part of the configuration. We won't be going too deep into any of the software, but we will be carrying forward the PCM 600 when we are doing our relay testing as well, right? Okay. So now we'll be looking at eSurgy Studio, right? So here I have eSurgy Studio open right in front of me, and I'm just gonna bring up the magnifier. Okay, so here is where you would be you'll be having your device, you'll be having your settings, and you'll be having the logic over here, right? So over this, you can see the different inputs, the different setting parameter configuration that you will be doing. What is the relay type? What is the relay model? What is the frequency? So on and so forth, right? But as soon as we pick up any particular protection relay, the first one that we need to do is we need to decide what are the protection elements that we want, right? So here, in terms of a MICOM P341, you can see what are all the different protection elements that is available here. So you can see power, you can see thermal, you can see overcurrent, earth fault, df by dt, vector shift, and so on and so forth, right? So you first need to decide what are all the protection elements that you want to enable and what are supposed to be disabled, right? So once you have done this, it would appear in the bottom of the screen, right? So here you could see all the different protection element that we have enabled over here. And the next step is, once you have selected what is the configuration or what is the protection element that you want, I would suggest you to go towards the CT and VT ratio. So here you would want to select what is the ratio of your primary voltage and the secondary voltage, and in case of any other checksync voltage sources or source inputs, or you have any residual voltage inputs, you can always specify over here. And the next thing is you have to specify what is going to be the primary ratio, the primary side of your CT as well as the secondary side of your CT. And you can always specify what is going to be the polarity of your CT as well. So once you have set all this, what you have essentially done is you have configured your inputs, that is your analog inputs, right? There are a lot more into this. You can set up your measurement, that is how do you want to display it, what is the measurement reference, and the next one we will be going is your binary inputs. So here you'll be setting what is the nominal voltage for your inputs. As we all know, voltage, DC voltage, that is how inputs usually function. And once you're done with this, you have to go towards your protection configuration, right? So in case of a 341, we have a system configuration. In case I could tell you, or I could specify what is the phase sequence that I want to specify, whether I have any VT reversal or not. So in case of VT reversal, if I'm swapping any particular phases, I can specify that as well. The same goes for CT reversal as well. Now for checksync, we have a lot of functions, but today I want to focus on one particular protection function, that is your very simple overcurrent relay. And I want to run a comparison between how overcurrent protection in case of eSurge Studio is different from overcurrent protection when you go towards your ABB relays, right? Okay. So the first one is you have your multiple stages of overcurrent relay. So you can see you have your phase overcurrent, you have your NPS overcurrent, that is your negative phase sequence overcurrent. But let's focus on only phase overcurrent for the time being. So you can see that you have your function that tells you what type of a curve that you want to use. So we have multiple types of standard curves, that is your IEC standard inverse, very inverse, extremely inverse, and so on and so forth. So I'm just going to select IET inverse over here, click OK. Then you can set a directional element. So if I want my system, or if I want my overcurrent protection to be directional in nature, or directional means forward or reverse, right? I'm going to specify non-directional. That's simple enough for the time being. And current set, right? So here the key thing to note is, am I setting the protection parameters in terms of primary or secondary, right? Every protection relay has their own way of defining it. So in case of eSurge, you just have, if you want to set it in primary, this is with respect to primary, right? You can see it immediately that because the maximum is in terms of kiloamps, we already know that this is the setting in primary. So if I want to set it in secondary, I just need to go to configuration and go down here. You can see our setting values, double click, select secondary, and the moment you have done that, you can see what is the setting current over here, right? It has just changed to 1. Why is it 1? It is with respect to your CT ratio, right? So your CT ratio was 300/1, right? You can see it is 300/1. So that is the reason why we call it as 1 amps, right? So here I have set my current. The next is your TMS, that is your time multiplier setting. So time multiplier setting will be specific only in case of curves, that is standard inverse curves. In case of definite time, you can see that it has automatically changed to time delay, right? So here I can set the relay should trip after a particular time in case of 1 second, right? So the concept here is, if the current goes above 1 amps and it stays there for a particular amount of time, in case of 1 second, the relay will trip within 1 second, or in this case, the overcurrent protection function will generate a trip output in case of current above 1 amps for more than 1 second. So we can always set it to be standard inverse. In case of standard inverse, it is going to follow the formula, that is, you can always refer the formula, and you have the TMS over here that is set to be 1, right? Now you can set more than one particular stage. You can have multiple stages. So one stage being your IDMT characteristics, and other stage being your definite time characteristics, right? So you can have multiple stages, but right now I'm just focusing on one, right? So once you have done or you have specified a particular protection function, the next one is how do I take this up forward, right? So I have configured my analog inputs. The next step is I have to configure my binary or digital outputs, right? So in case of MyCom, we know that there is something called PSL. So all I need to do is just double click PSL and it just opens up over here. Yes. So here is a very simple logic that has been given over here. So I'm just going to zoom in over here. Right. So you can have multiple sizes over here. So here you could see the opto inputs are mapped. So you can have multiple inputs. So here it is configured for selection of your setting group. It can be used for blocking your earth fault or overcurrent protection. It can be input can also be used for resetting your relays or LEDs. So in case you want to reset your LEDs. Now input here and the last two you can see over here, it refers to your breaker contacts, right? So if a breaker status, if I need to give it as an input, I can give it as an input to my protection relay. The next one is, do I want to configure any of your output in case of fault triggers? Yes, I can do that as well. The next one that I want to look at is your, is going to be our output relays, right? So if I just move this side, so I can see the different protection element that is available over here. I can configure it as a general trip, like I already mentioned. So, but more importantly here, you can see that this is my I greater than 1, right? So that is the stage 1 protection element that we have set, stage 1 overcurrent protection. Now it is configured to my output, that is R3 over here. So please note that 1 here represents your OR gate. So I can always show you like this. So you can have one that is represent your OR gate over here. You can also have multiple gates. You can have AND, you can have flip-flops, things like that. You can even have a programmable gate on the top if you're able to see. So here you can select your AND gate, your OR gate, your programmable gate, and your latching concepts, right? So, but more importantly, what I need to do is based on my particular operation, based on what is my schematic diagrams, I have decided that the overcurrent stage 1 should be given for output number R3, right? That is relay number 3. Now moving a bit more down, we can see that there is also some annunciation and LED mappings. So I can configure a general trip, I can configure a phase by phase trip, or I can configure a particular LED for a particular protection functions, right? So here I have configured my greater than 1, that is stage 1 overcurrent OR gate as my LED number 2. Now this is of latching type. Now what is the steps that we have done till now? So we have taken into consideration about what is my analog input configuration in case of CT and PT. We have configured what is my binary inputs and binary outputs. So in case of binary inputs, we had our breaker contacts, we had our blocking signals and setting group selection. In case of binary outputs, we have configured different a general output through an OR gate for all the protection functions. And at the same time, we have configured LEDs for a particular LEDs based on the protection functions. So once this is done, all you have to do is just I'm not saving anything. All you have to do is just go back to your protection, go back to your eSurgy studio. So once eSurgy is done, so all you need to do is just send it to the protection relay, right? So this is something that I feel that a lot of protection engineers will be seeing it in a very easy to use kind of a way, right? But because there is not much of a logic involved, you just need to connect a particular protection function to its own particular inputs or outputs, and you can need to give the settings as per your recommendations, and you need to set your analog inputs configuration, right? Now let's move on to ABB, right? So in case of ABB, the relay that we have over here is your REG650, right? So REG650 is actually a generator protection relay. So we will be covering the generator protection relay now. So all the testing that we'll be doing is in this relay. And so here you could see that I have two things. One is my IED configuration and the next one is my application configuration. So if I right click a particular element, I get two things. One is my parameter setting and the other one is application configuration. Now in case of ABB, the application configuration is pretty exhaustive. As we could see over here that there are a lot of configurations that needs to be done in case of ABB because ABB, you need to be configuring what is the analog input, how it is going to be used, what is going to be the cycle, what is going to be the execution order, things like that, right? But from a parameter setting perspective, ABB also follows the simple rule of what we saw in case of MyCom, right? So the first thing that I have to set is what is going to be the hardware configuration. So hardware configuration is going to be the names for different cards. So ABB in ABB relays, you have different input and output cards as well as analog cards. So you need to be setting what is the input card. So here you can see that in the TRM, I have different CT ratios. I have multiple CT ratios and multiple voltages that I need to set over here. And I also have another card, this being a generator protection relay for differential protection. We have a lot of current inputs as well. So here you could see that I have given a name that is gen terminal IL1. That is this represents the current from the generator terminals R phase, right? So you can see that the CT ratio is set at around 1600. You can set it in any possible way. You can see what is the range minimum to maximum that I could set over here. I can have on the neutral point, I can have multiple CTs, and I'm also having the residual voltages as well as check sync voltages over here, right? On the other side, I need to set the time, but in case of ABB, there is a very simple thing that you need to think of, right? You need to think of what is going to be the frequency that you need to be setting. So here you can set what is the frequency, but more importantly, you need to be setting the base values, right? So base values, all the settings that you give, all the protection setting that you give are based on your global base values. So I can have up to 6 global base values, and each global base value will have a base voltage and a base current as well as a base apparent power, right? So what I have essentially given over here is I want to give my settings as a representation of my full load parameters of my generator, right? So the base values here represents what is the full load of my generator. So under normal working condition, under full load of my generator, I know that the full load current or the rated full load current is around 1522 amps. So I'm setting that as my base value. So all the settings that you will be providing in ABB will be based on these base values, right? So that is the key thing that you need to know as compared to ESRG, where we will be setting, or in case of MyCom, we will be setting all the settings, your parameters based on your CT ratio. In case of the PCM 600, you will be setting it based on the global base values that you specify. So in case you want to make it to be equal to your setting CT ratio, yes, you can just change this to be 1600, and now the base value is equal to your setting value or CT primary ratio, but I want to set it as a function of my full load current, right? So I'm just going to set it as equal to my generated full load current over here. Now there are a lot more of settings over here. You have your communication settings. You can also have your reference channels. So when you want to compare what is your phase angle, so here you can see that I have set the channel number 7. Usually voltage will be set as your reference phase reference angle. So this is for assuming that whatever the angle at this channel, that is TRM channel number 7. So I just need to go to TRM. You can see TRM over here. I need to go to channel number 7. So you can see channel number 7. That is my generator terminal voltage. So that is 11 kV bar 110 volt. So whatever is going to be your voltage or the angle at channel number 7, that will be set as 0° phase angle, right? All the other parameter will be calculated. All the other phase angles will be calculated based on this channel, that is channel number 7. Now, for going into your protection settings, you need to go into application configuration. So application configuration, there is a bit more into your analog modules as well. So I can not only set what is the type of on the ratio, I can also set what is the DFT, what is the global base value that you want to use for that particular this thing, for the particular channel, what is the type of input. So I can set the input to be current or voltage as well. I can also set what is going to be the connection, whether it is a phase to neutral or a phase to phase connection as well, right? Now the next thing that I want to set is my protection, right? So you can see that there are multiple protections. Now the protections are classified based on the page of your application configuration, right? So you can see that in the bottom there are the pages that is shown over here. So you have analog inputs, you have your inputs, you have differential protection, right? These pages will be shown over here, and what is the block within each page, that protection function will be available inside, right? So you can see differential protection, gen pdiff is the generator differential protection block that is available in page differential protection. So I just need to go to differential protection. Inside that you can find the block gen pdiff. Now today we'll be looking at the generator backup protection. That is a current based protection that I want to look at. If I have multiple protection, all the protection function will be listed over here. So today I want to focus on the generator terminal overcurrent. So it is very simply measures what is the current in your generator terminals, and if it is greater than my setting value, then the trip and the pickup signal will be generated. Okay. So here you could see what is the block, that is you can see page generator protection, generator backup protection, current, gen TRM OCR, right? So here you could see the block. Now this block has multiple inputs. So everything on the left hand side is going to be our inputs. Everything on the right hand side is going to be the block outputs, right? So I'm going to have a current input over here. So this is going to be the 3-phase group signal for my current input, and there is not going to be any voltage signal because I do not want any directional. I'm just going to say it as off. And on the output side, I have taken a general trip, right? This is going to be a general trip. If I want phase specific trips, I can take that as well, right? And if I want a pickup signal, that is my general pickup, I have taken it as a general pickup, right? So this is going to be there for all the protection elements. So stage 1, stage 2, stage 3, everything is available over here for you. Now to go to the settings of this, all you need to do is just, you can either do this, you can just go right click and go to parameter setting, and you can see that the parameter setting is open, or you can just keep parameter setting opened over here and you can just go into this, right? So now what we have done is I have to first select the global base, right? So you remember that we have 6 global bases. So in the first one is what I have set to be the full load current, that is 1522 amps. So I'm setting my overcurrent protection also based on the global base number 1. Measurement type, I could select whether I want to be a DFT or an RMS value. DFT is mostly the best way of carrying forward. Now remaining everything looks very similar to what we saw in MyCom. So here you could see what is going to be the directional mode. I'm going to have non-directional or forward or reverse. I'm also going to have the characteristics. So characteristics here would define your curve, right? I could have different type of characteristics. I could even have definite time over here. The next one is going to be your operate level or pickup current. So here we have set it to be 120% of base value. So here you can see that IB here represent your base value, that is 120% of your base value. So 120% of base value, you just need to go here, 120% of 1522 amps. That is going to be your actual setting, right? And the next one is going to be your time delay. In case you want to give a definite time delay, I do not want to give any definite time delay. And the next one is your TMS, right? So I'm going to give a same TMS of 1. There are 2 more settings that is involved. What is the minimum operate current? So do I need to have a minimum operate value? And what is going to be the minimum operate time, right? So I can either set it to be minimum operate current and minimum operate time. The curve is still going to be followed as per normal inverse pickup as 120, but I can also say that I can have a minimum operate current of something bit more than 100, right? So this setting is going to play a major role if this if the 100 is more than 140, right? So even though the curve starts at 120, my relay is only going to operate after 140 because I've said that the minimum is going to be 140. Now I can make this equal or less than the setting value, so I ensure that only the setting curves are followed. Now similarly, we can have multiple steps. So I can have another element that is stage 1, stage 2, stage 3, stage 4. So here I have only enabled only up to stage 1, right? So once this is done, so what have we done till now? In case of ABB, we have just configured what is going to be the inputs. We have configured what is going to be the CT and the VT ratios, and we have configured what protection element I need to use. And the last one is I have configured what is the settings that I need to give, right? So to go to inputs and output configuration, right? So you can see here that every block is going to have its own inputs, right? This is a signal that is generated only when the overcurrent protection trips. So this is a general trip. So I can use this signal to a lot of places. So I can just go here, right click and go to partner. You can see that I'm using it in multiple trip logics. So I'm going to use it as a part of the trip logic. So you can see that in case overcurrent trip comes, it is going to go towards a particular output, right? So it is going to generate a signal called circuit breaker trip or the generator circuit breaker trip, and it is going to be used for particular generator circuit breaker trip. Now I could have multiple functions, and this is what we call as the trip logic of the generator circuit breaker alone. You can have multiple trip logics. Like if you go down, you can see that there is a trip logic separately for the field circuit breakers, similarly for the turbine as well as for the grid side as well. So we have used a trip logic. We have configured my, you can see that this is my overcurrent protection. I've configured it for a particular output as well. Now in order to see what is the pickup, I'm just going to right click here and I'm going to use it as in disturbance recorder. I can see that a lot of inputs are being used for disturbance recorder in case of external trips as well, right? So now I have configured my input as well as my outputs. So pickup I can either use for disturbance recorder or I could use for alarm as well. Now alarm I could use it for a particular LED. It depends on where you want to use, what is your schematic says. Now in case of PCM, what I have done is I have first configured my CT ratio in hardware configuration. You can just go to the parameter setting. I've configured my CT ratios over here, and I've also configured my global base values. So global base values in this case would be a representation of your circuit break, or generator full load current. The next one is I have configured what are the different protection functions, and I have set or given the settings for the protection functions. In order for you to enable a protection function, you have to go insert the block, right? So if the block is not inserted, then the protection function will not be enabled for you, and you will not be able to see it in the menu that is on your left hand side, right? So once I've done this, I have configured what is going to be the outputs, that is my trip as well as pickup outputs. And you can have multiple block signals. So if I have a particular input, either as a digital input or an internal relay generated input, I can use it for blocking a protection function as well. I can block the entire overcurrent protection function by giving an input of the block, or I can block a particular stage of overcurrent protection function, right? So this is a very simple way of deciding or configuring your ABB protection relays. Now the types of configuration, the different types of blocks that are available will change based on the relay that you are configuring. But from a very generic perspective, this is going to be your relay configuration in terms of ABB using PCM 600, right? Okay. So moving ahead, right? So this was very simple about protection relay configuration, right? Now, what do we actually talk about protection relay testing, right? So that is what we are all here for. So protection relay testing, or what we call as secondary injection testing, is mainly the use of a particular equipment. In case of me over here today, we'll be looking at the Omicron CMC to inject certain parameters into the relay from the secondary side of your instrument transformers. So the reason why we call as secondary injection testing is because we are injecting it from the secondary side of your instrument transformers, right? Now, the most important thing that you need to understand is how we saw the protection relay as a very generic way, in a very generic format, irrespective of what is the type of protection. Similarly, we'll be looking at a protection relay test kit as well, right? So a protection relay test kit is something that is very simple. You just need to understand what are the different parameters that you will be injecting. So every single parameter or every single protection relay will demand a certain parameters, right? So the four main parameters that you will be looking at is your voltage, current, frequency, and phase angle, right? So voltage, current, frequency, and phase angle can give you any kind of a parameter that you would want, right? So for example, if I have a test kit that could inject any voltage, any current at any frequency at any particular phase angle, then I can inject not only individual voltage, current, frequency, but I could also combine multiple parameters such as voltage and current to inject different inputs such as power. In case of voltage and current, I can give power. In case of voltage and current, along with phase angle, and I could give impedance. But at the same time, I could also specify your frequency, your symmetrical components. A lot more of things is possible when you're using just these four parameters, right? So please try to understand that whenever you have any protection relay in front of you, try to understand what parameter will you be injecting and how do I inject it in terms of these four parameters, right? So to inject a particular power at a particular real power and reactive power, you can just combine voltage, current, and phase angle. So the calculation that you need to do is how much voltage and current at what phase angle I must inject to get to the required power in case of real power, in case of reactive power. So how do we actually go into that? Okay. So moving ahead with secondary injection test kit or secondary injection testing, there are a lot of equipment that is available over here. So you have your the SMRT from Megger, you have your Omicron CMC, you have your ISA test kit. You also have a very basic auto transformer based testing equipment as well. So today we'll be focusing on the CMC 356, right? So CMC 356 is one of the most commonly used test kits out there. So it can inject up to 32 amps per phase of current, and at the same time it can have multiple different configuration. It has a very sophisticated software that we'll be looking at now, right? Okay. So before jumping into the test plan, what I want is to just go a bit more into the software of Omicron itself, right? So I'm just going to open test universe. So what you're essentially seeing on my screen right now is the Omicron test universe, right? So Omicron software is called the Omicron test universe. So you have multiple test modules for performing functional testing. So each module you'll be using for a different particular function. At the same time, you can have testing of your power utility communication, that is your substation automation system. You can also use system-based protection testing. But today we'll be looking at a very simple example from Quick CMC. So Quick CMC is one of the most easy and the basic way of starting your protection relay testing. So before we do that, we need to ensure that my test kit is connected to my system. So the first thing that you'll be doing is going to test set association. So once we have test set association, this is something, the device link is going to open up and you can see that it is ready. Everything is good to go, right? So I just have to click Quick CMC, right? So Quick CMC is a virtual front panel type. So you have access to the main 4 parameters, that is your voltage, your current, your frequency, as well as your phase angle, right? So this is the main view of your Quick CMC. So you can see whether your test kit is connected. Yes, it is connected, but the outputs are not active. And you have your test view over here. So in test view, you can have your voltage inputs, your current inputs. You can also have binary inputs and binary outputs as well. Here on the right hand side, you can have your phasor view. You can have your impedance view, and you can have any particular report that we generate, right? So before we start off with actual injection, the first thing that we need to know is what is the steps that we need to take in order to have a successful testing, right? So when it comes to Omicron, you will be looking at the Ohm law or the OHM, right? The Ohm law. So the O stands for object configuration. So you can see over here that we have something called the object configuration, that is the test object configuration. The H stands for hardware configuration, and the M stands for module configuration. That is what we will be doing over here, right? So as soon as you click test object, you're going to be greeted with the device settings. So what do you actually do in test object is you specify what is the device setting. So in my case, I'm going to use a generator protection relay. I'm just going to give a name, and device type is going to be again a generator protection, and I can have a particular serial number and a particular model number, name of the substation, which bay it is connected. But more importantly, for ease of use, we have the nominal values, right? So what is going to be the nominal values? So in case of primary current, I'm going to have the secondary is always going to be 1. That is what we have done in the PCM as well. The primary side, I'm going to be having 1600, right? So this was the CT ratio that we gave in your protection relay. So I'm just going to click OK. And top of this, you have other device properties, like you can set what is going to be the maximum current that could be injected, and you have your debounce or deglitch time. So I'm just going to click OK. And this is pretty much it. When you're doing in Quick CMC, this is pretty much it. For more advanced, we will be looking advanced sessions. We will be looking at what is function, what are the different blocks that we could do, how do we import and export relay settings, what is Rio, what is automation, things like that. So those are scheduled, but for today we'll be looking at this, right? So I'm just going to click OK. So once this is done, my O for object configuration is perfect, right? The next one that I need to look at is hardware configuration. Now hardware configuration is very important when you want to ensure that you have the right test set connected. If I am in a network, I can have multiple test kits connected to the same network. But at the same time, I specify what is the outputs and inputs that I want. So today we'll be testing the overcurrent relay. So it tells me that, okay, yeah. So I'm going to be testing a very simple overcurrent relay. So I'm not going to be using any voltage. So I'm just going to specify this to be not used. Now here you can have multiple configurations of your current outputs as well. So I can have all the 6 current outputs, or I could have a particular 3, that is channel number B, or I can have channel number A, or I could have paralleling of both the channels to give me 64 amps at a higher burden. I could have a single phase 128 amps if I connected in such a way. Or this is something that a lot of people don't know. If I'm testing both overcurrent as well as an earth fault protection, I could have IE that is automatically calculated. So you can see over here that IE could automatically calculate it. So if I'm injecting the phase currents from channel number A, 1, 2, 3 and N, from channel number B, that is 4 and N, the earth fall current or the neutral current is automatically calculated by Omicron itself. So it kind of makes your life simpler at that particular time, right? So I'm going to have current output number A over here. I'm just going to select it. So I'm just going to click OK. Now, the moment I go to analog input outputs, here I can specify what is the type of output signal, right? There are different types of output signal. So please be very careful when you are selecting what type of output signals that you want. For example, if I want to say that what I'm injecting is I0 or zero sequence, I can specify it as I0 directly. If I want to use it as a generic current injection, please select one of the I parenthesis 1, I1, I2, I3, I4, right? These are very specific to Omicron itself. So IR is a very generic module again. Now I can change the display name to whatever I want. So we know that this was the terminal L1. So I'm just going to keep it as terminal L1. I'm going to say this is TRM L2 and this is TRM L3, right? So this is just for ease of my use, right? I can also specify what is the connection terminal that I want. So if I know what is going to be the CT number, so I can specify what is going to be the CT number and or TB number terminal block, any connection terminal that you need to give. Once this is done, you need to set your binary analog inputs. So any binary output from the relay. So if I say a trip output or a pickup output is an input to your Omicron, right? So the output of your protection relay is an input to your CMC or your second injection test kit. So whenever we talk about binary inputs, please understand that they are outputs of your protection relay, right? So what I have done is in the PCM 600, you saw that we have configured a particular output for trip, right? So we have taken that output and we are giving it as an input to my Omicron as binary input number 1. I have taken my pickup, that is my start function, as binary input number 2, right? Here I can also specify whether they are potential free or potential contacts, that is wet or dry contacts, and remaining everything else is not used. I'm not using any of the other 10 outputs. So Omicron has 10 binary inputs and 4 binary outputs. I'm not going to be using any of those. And binary output also I'm not going to be using because we are not giving any output from the Omicron. So if I want to generate any particular input signal to my PCM, I can use the binary output that is available from Omicron itself. I'm not going to be having any DC analog inputs as well. So the moment I click apply, you can please note the screen that is on this side. You can see that now the screen has changed. So here it is showing me Gen TRM L1, Gen TRM L2 and Gen TRM L3, right? So this is how you get what you need. Only those should be present in case of your analog outputs. So analog outputs are going to be your current, the 3-phase current. In case of the ABB relay, we set it to be your terminal phase currents, right? So I am using it as output from the Omicron and given it as an analog input to the relay. Now to inject, it is very simple. Just enter a particular value over here. So if I want to inject it 1 amps, I could just inject as 1 and press start, right? So the moment I've pressed inject, you can see that the corner, this one has changed to saying that my CMC outputs are active, right? You can also see that the start signal is the relay, the Omicron CMC is injecting. To stop injection, just click stop, right? So now the next thing is views, right? So this is where things get a bit more interesting. So some people would prefer to inject in terms of secondary values. Some people would prefer to inject in terms of primary values, or some people would inject it in terms of reference values or relative values, right? So to check that, all I need to do is select my units over here, right? So am I seeing this as primary or am I seeing this as secondary? So if I select primary over here, you can see that it has automatically changed to 1600 amps. So the 1600 amps is the setting value or the CT ratio that we have given in our device settings. So if I just go to test object and double click device, you can see that I have set the primary is going to be 1600 amps or 1.6 kilo amps. I'm just going to click OK. And if I want to see it in secondary, I just select in secondary. Now I can also see it in terms of relative to what, right? So if relative to primary, I can see it as relative value. So it's 1 times the primary current, right? So I can set it to be 1 times something in terms of per unit or in terms of relative, because we have the CT ratio to be 1600 bar 1. We are obviously going to be getting 1 times your relative over here. So if I say that, okay, I'm just going to give 0.5 times the nominal current in primary will give me 800 amps, right? So I just click absolute over here. You can see that it has calculated or it has changed to 800 amps. So I can also measure the time in terms of seconds or number of cycles based on your frequency. So for the time being, I'm just going to select it as secondary and absolute. Right? Now there are multiple things that you could still do. There are some certain shortcuts. So I just need to right click, and the moment I right click, you can see whether I want to set it equal to nominal value, that is 1 over here, or if I want to set it to equal magnitudes, that is, if you're right clicking a particular thing, all the phase parameters or all the parameters of that particular channel will be set to 1 amps, right? Or equal to whatever this is. So if I say that this is supposed to be 0.5 and I right click and I select it equal magnitudes, you can see that all the three has become 500 milliamps. So right now I can also specify it to be 50% load, that is 500 milliamps, or 100% load, that is 1 amps, and unloaded, that is 0. So in case of, if you are using voltage as well, in case of loaded, unloaded and 50% load, you will be getting the voltages as well. But here we are injecting currents only, right? So once you have done this, you can see everything that is present in your phasor, that is present over here. You can also see it in your phasor view. So this is going to be a phasor view. This is going to be the real and imaginary part as well. Now the next thing that you can look into, I'm not going to be going too much detail into this, is the set mode, right? So you can set a particular parameter directly. That is, you can directly inject what is my what is going to be the current and the voltages, or I can set it in terms of line to line, in terms of symmetrical components. I could use in terms of powers or fault values. I could set it based on how I want it, and Omicron automatically calculates what is supposed to be my actual value in terms of current, voltage, frequency and phase angle, right? So this is a very short introduction about the Omicron CMC, but now we'll be quickly going into how do we actually test a protection relay and what is the method for testing a protection relay, right? So before jumping into that, I'm just going to go into a test plan. So whenever you enter a particular site or you're going to start testing, you always need to have a particular fixed test plan in your mind. So the first step that you will be looking at is you need to get the relay settings, the drawings, what is the application that you need to that you're using it for, what are the protection functions that you need, and you need to create a checklist of all the elements, all the protection elements, all the outputs and all the signals that you need to test, right? And you're also supposed to, in case you're doing it live, you need to isolate the current and voltage input, and you need to connect your test kit as per the recommended schematics. Once that is done, the first thing that you'll be doing, you will be checking the measurement, right? So you need to check whether the connection that you have made is correct. You need to perform a measurement test and you need to record the results. So then choose the protection element that you want to test. So in our case, we will be testing the overcurrent protection now. So try to understand what is the basic operation, right? So if we have selected an overcurrent protection element, try to refer back to the block diagram that we saw. What is going to be the functional logic? What is the inputs that is necessary? What are the output that I am going to do? And the first thing that you will be doing is what we call as a pickup test. And once you're done with the pickup test, you need to do the timing test, right? So these are the two main tests that we will be looking at. So this is the overcurrent logic behind behind the ABB REG 650. So very simply, it measures the phase current. If it is exceeding the pickup or the start value, then the relay picks up, and after a particular time based on your curve. So in our case, we have selected it to be an IDMT characteristics of TMS1 based on the output, based on your timer. The time is selected and the relay trips after a particular time. Once the relay trips, the operate signal or the trip signal is generated. So what we have done is we are injecting current from your Omicron, right? And we are measuring what is going to be the pickup value, right? At what point does the relay pick up, and at what point does my relay operate? What is going to be the operate time, and how does it compare with respect to your calculated parameters? So this is the very generic connection diagram. So we have our current outputs. We have connected to current output number A, and on the other end, we have connected it to the relay as per the given schematics, right? So I have connected the generator TRM to my current as current inputs. I have configured one of the output for trip and one of the output for pickup as well. So once you have wired as such, the first thing that we need to do is do a wiring check, right? So before we do a wiring check, we need to ensure that my kit is switched on, my kit is communicating, and my relay is also communicating in case I want to see the parameters live. So once all this is done, I need to perform the measurement test, right? So the first thing that before doing any of this, we need to understand, like we already mentioned, how the relay behavior is supposed to be. So what should be the expected pickup, what should be the expected trip time, and how we are actually going to test, what test points we are going to select. Everything needs to be decided beforehand before we actually start the testing, right? So this shows the picture of your REG 650, and what we are going to do is, we are just going to start testing, right? So I've already made the connections as per the connection diagram that is given over here. And once the connections are done, I'm just going to go into my Omicron CMC over here. So here you could see that we have already configured it. First step is object configuration, right? The next step is hardware configuration, and the third step is going to be our analog inputs, right? So right now what I want to do is I want to inject single phase, right? And there are two ways of doing this. One, I can see in PCM itself. If I have already configured it, I could easily see what is going to be the input current and output current, or I could see it from the HMI of the relay itself, right? So the first step is input configuration, right? So we have done our object and hardware configuration, right? So here what I have here is a very simple Excel sheet about what is going to happen and what is the expected results, right? So here you could see that I have specified what is the CT ratio, right? So this is 1600 by 1. Now the base current we have kept it is 1522 amps, right? So this was from your PCM. So I'm just going to go here. So you can see here that the base current is set to be 1522 amps. So I'm going to be using this over here. Now I need to know what is going to be the pickup current, right? So pickup current is, we can select it from here. So here I have selected this pickup current to be 120 times the base current, and base current is 1522, right? I'm just going to go back over here, and you can see that with respect to primary, the pickup current is 1826.4 amps, right? How do we calculate this? This is nothing but 120% of 1522, right? So 120% of 1522 will give me 1826.4 amps. Now what is going to be the expected pickup? So in terms of secondary, now secondary we need to compare it with respect to the CT ratio, right? So the secondary here is nothing but the primary, the pickup in terms of primary divided by the CT ratio. So we know that the pickup is supposed to happen somewhere around 1.142, right? So that is the first thing that we will be looking at. So all I need to do is go to Quick CMC. So here I need to ensure that I have selected my start as my input trigger. So here I have selected pickup as my trigger. So once the trigger comes, that is once my relay generates the pickup signal, my kit or my injection will switch off, right? So there are multiple ways of doing this. So I can directly inject a particular value, or I can step it or ramp it. So this is a very or a much cleaner way of actually doing your pickup test. So in this case, what you'll be doing is you'll be selecting a signal, right? Here I'm just selecting L1, right? And I'm going to be stepping it up in terms of magnitude at a step size of 0.001. That is 1 milliamp I'm going to be stepping up, right? So I'm just going to increase it to 0.1. So every time I click this up arrow, so I've clicked it once, you can see that it has become 1.010. I click it again, it has become 1.020. So you have a much finer control of injecting it rather than you typing up those values itself. Now this is going to be step. Ramp on the other hand is I can just give it as auto step, means it is going to increase automatically by 10 milliamps every 1 second, right? So it is going to increase it automatically by 10 milliamps every 1 second till my trigger has come. So the moment trigger has come, the ramp will stop and my injection will switch off. So I have not started injection. So I'm just going to click up. You can see that it is automatically increasing on its own. So if there is an auto ramp that is running, then the whole area becomes grayed out. So if I just stop this, you can see that the whole area is now white. Now if auto ramp is running or auto step is running, you can see that the whole area is now grayed out. So we already know what is going to be the expected pickup. So I know that my expected pickup is going to be 1.142. So I do not need to start at 1. I'm going to start at some value close to 1.142. So I'm just going to say start at 1.1, right? And increase the size by, I'm just going to say 1 milliamps every 300 millisecond, right? So now what I'm just going to do is I'm just going to start injection and I'm going to press up. You can see that the current is automatically injecting, right? Now this is incrementing at a rate of 1 milliamp every 300 millisecond, right? Now all we have to do is just wait for the feedback to come over here. So when the moment the feedback comes, you can see that the feedback has come, the pickup signal has come. It has picked up in 86.50 millisecond. And you can see that the kit has stopped injecting. You can see that the start is not green anymore. And this value that is shown over here is your pickup value, right? Now this I can just make it 0. Now I want to do it for the next phase. I'm just going to give 1.1. So now I know it is picking up somewhere around 1.4. So I can start it off something bit closer. If I want a much more finer value, I'm just going to kind of increase the step size, step time, and signal. I want to inject L2, that is Y phase. I'm just going to change it to L2, right? So again, I'm going to start and up arrow. You can see it is automatically injecting and you can see whether a trigger has come or not. You can see that the trigger has come and we get around 1.139. So what I can right now do is I can just go back to the Excel and I can say that I got a value of 1.139, right? So this is going to be a deviation in terms of percentage. That's going to be minus 0.25 from your expected value of 1.142. Right? So this is very simply what is my pickup value. So we have tested the pickup value as per my settings and I'm happy with it, right? That's it. Now the next thing is, how do I test the timing test, or how do I perform a timing test? So I know that I have set it to be a standard inverse curve of TMS equal to 1. So this is the formula for a standard inverse curve. So you can see the formula that I have just pasted it over here. So it is nothing but TMS, that is 1, into 0.14 divided by the ratio of your fault current by setting current raised to 0.02 minus 1, right? So your curve is going to look like something like this. So I'm just going to do this. Yeah. So you can see that this is how my curve is going to look like. This is going to be the standard inverse characteristics. Now all I have to do is I need to check points within this curve, right? So I can choose multiple points, or I can choose a particular current, and I could measure what is going to be the time on the calculated versus actual, right? So I can do two things. Either I can set the ratio. So if I say that I'm going to be injecting a current that is 2 times the setting current. So what is the setting current? Setting current is 1.142. So if I want to inject 2 times 1.142, that is going to be 2.284, right? I can do that, or I can select an injected current. I'll say that I'm going to be injecting a particular current value in terms of amps, and I can calculate what is the ratio. So this ratio here represents your IR. IR is nothing but your fault current by setting current, that is fault current divided by pickup. So calculated, it is nothing but 2 divided by 1.142, right? So this is going to be the expected pickup, right? And I'm going to be calculating the trip time based on this particular formula, right? So I've calculated what is the trip time. Now all I need to do is measure the actual trip time and find out what is going to be the deviation, right? So I can select multiple points. So here I have selected 5 points. All I need to do is just inject these currents and measure what is the trip time. So to do this, I don't need any ramping. I don't need any particular stepping. So all I need is, I need to ensure that my trigger is my trip, not my pickup, right? So I just need to go inject a particular current. So I'm going to be injecting in one phase, and we know that from the Excel sheet, if we can see that the calculated trip time for 2 amps is 12.41 seconds, right? So I'm just going to go here, and I'm not doing anything, just press start. So the moment I press start, you can see that the relay has picked up. If it is red, it means that the signal is high. The relay has picked up, and you can see that the time is running over here. And now the relay is going to trip, and it has tripped in 12.41 seconds, right? So now the relay has actually tripped in 12.41 seconds. Now this is for 2. Now I can do the same thing with respect to 3. I can do it for all 3 phases. So I'm just going to click start. You can see that the relay has picked up and the time is running. So you can see that the injection is going on, and the moment the relay has tripped, injection has stopped, and you can see that the relay has tripped in 7.201, right? So our calculated values was, this was 12.41, and here is 7.201, right? Now it's just a very simple formula. You can see what is going to be the deviation in terms of percentage from your calculated values, right? So I'm just going to inject one more point. So I'm going to inject, let's say 5 amps on all 3 phases, right? So here I have injected 5 amps on all 3 phases, and I'm going to press start. You can see it's green. You can see that the kit has picked up, or the relay has picked up, and I got a trip signal, and the time is 4.696. So I'm just going to go back to the Excel sheet. I've injected 5 amps, 4.696. Now similarly, I could have multiple points. I could test multiple times, and in the end, I could also plot what is the test results, right? So here you could see what is the actual versus calculated. So you can obviously make it a bit more visible, but the simple thing is you can see that the dotted line is your calculated value and the orange line is your actual, and there is a very small deviation between all of them, you can see that we got a deviation of somewhere close to 2 to 3% at max, right? So this is very simply how you would do a timing test. So what have we seen today? We have seen how using quick CMC, how do we configure the test object? How do we configure the hardware? That is hardware configuration. You select what type of hardware that you would want, what configuration of hardware that you want, and how do we select the parameters, on what basis do we set those parameters, and on what basis do we do the pickup test, how do we assign binary inputs, how do we assign triggers. And on the relay side, we have already seen how do we actually calculate the actual, or how do we calculate what is going to be the relay behavior, what is the expected relay behavior, and how a relay performance is with respect to your expected relay behavior, right? I can also plot any of the results. So these are very simple Excel. I think anyone could do on their own. But the key concept that I want to point out over here is people should try to understand how testing needs to be done and what should be the testing methodology that should be followed before you actually start the injection of testing itself, right? So now, once you have done the testing, so what you have done is you have completed the testing, you have taken care of all the results. At the same time, you have also taken into consideration what is the deviation with respect to your actual behavior as well. So once you have done all of those, essentially you have completed your testing, right? So again, thank you for a lot of people for being over here. A lot of people have actually participated, and we are having a consistent watch time and a consistent number of viewers. And if you have any questions, please put them on the chat. I would be glad to pick up questions as it comes forward. And in case you have any more questions, you can always keep putting them on the chat. This video is going to be available to you once the session has completed. And we also have a lot of programs that we have planned in the upcoming future. So I hope that people would subscribe to this channel. I hope that you like this video and what we have done today. And what we have planned is we are planning for events every Sunday. So I just wanted to kickstart this with a very simple basics of protection relay testing. As we go forward, every week we will be going through a bit more deeper, a bit more advanced concepts. And next week on the 13th, we will be having the part 2. That is, we'll be going a bit more deeper into relay configuration, and we will try to test the same protection function along with modules such as state sequencers, such as ramping. We'll also be looking a bit more into relay setting calculation, like how do you actually calculate these relay settings. And on the week after that, we are planning for going towards frequency protection. A lot of people are having concerns about this. So we just want to do it in the best possible way. We'll be looking at overcurrent and over frequency and under frequency, as well as, rate of change of frequency using the latest standard. So 2019, the rate of change of frequency protection standard has been updated. There are a lot more things that you need to look forward, in with respect to DF by DT and ROCOF. So we will be looking at that on the June the 20th. And on 27th, we'll be looking at voltage-based protection, right? So voltage-based protection is not only just over voltage and under voltage. We also want to have a look at voltage controlled overcurrent, right? So there are a protection called voltage control or voltage restrained overcurrent. We will be looking into that as well. And fuse failure, any kind of secondary system supervision, those also come under voltage-based protection. So we will be looking at how those protection functions are. We'll spend an hour and 2 hours around based on this, and we will be looking at this for this week's. We'll also have these are live events, so we are also planning to include a couple of more offline videos. so that you could look at it whenever you want. So I would suggest that please subscribe. Please follow us on YouTube. You can always follow me on LinkedIn and follow the company on LinkedIn so that you get your updates as much as possible. And we will be having a lot of content coming more. This is just the start. So we have just started it today. And we have a lot more of content that we have planned both in live as well as scheduled posts. So thank you so much for being over here. In case you have any questions, please post them in the chat. You have any comments, any opinions from you is appreciated to the maximum. In case you like this, please like it. Please also tell us why you liked it. You can always contact me anytime regarding any of your questions. And you can follow my blog at phillyelectrical.com. And I'm very active in LinkedIn, as a lot of people know. So thank you again. This is Saravnan from Minatal Power Systems, Chennai.